This reaction called catalytic hydrogenation. From the name, we know that we're adding hydrogens. So each of the carbon from the carbon-carbon double bond, those carbon, each one will get one of the hydrogen because it is adding the same atom, same hydrogen. So there is no regional selectivity. The two carbon get the same thing, hydrogen. And there are no anti-Markov-Nikov or Markov-Nikov addition. So for example, if we start with this alkene and we use hydrogen, so for this reaction, usually it will run at a very high pressure and always excess amount of hydrogen, meaning that you cannot control one equivalent or two equivalent hydrogen in here, and it will go with catalyst. So the more expensive catalyst is called platinum, and more commonly used is palladium on carbon. So either one will work. And the outcome for this reaction is from alkene to alkane, and fully saturated because you add hydrogens that the oxidation number of carbon decrease. So this is a reduction. And this reaction is very efficient in the presence of catalyst and usually 100% conversion. And we need to look at the stereochemistry of this reaction. So imagine this is your, I'm drawing this here. So this is your catalyst, okay? This is the platinum, for example, and this is all the atom bonding together, really organized. And your hydrogen will be very nicely aligned on here. For example, we have hydrogen, this is hydrogen gas, right? They will this is one hydrogen gas. So when your alkene comes in, okay, so this hydrogen will be on the same side of this two carbons. So that means when it's added onto it, will be a syn addition. So for catalytic hydrogenation, it is syn addition. So if you start with this molecule right here, let's see how we can show the syn addition. So we use hydrogen with palladium on carbon. And for syn addition, your hydrogen will end up on the same side, meaning that your acyl and the methyl group will end up on the same side as well. So we will draw them either all on the dash or on the wedge. So if you want to show the hydrogen, you are welcome to that. These two hydrogens will be on dash, and these two hydrogens will be on wedge. But usually for bond line, we don't show the hydrogens, but that will dictate where other groups will be. So that is the catalytic hydrogenation. We need to think about the stereochemistry. It is syn addition. The next addition reaction of alkene is called halogenation. From the name, we know that we are adding halogens. Specifically, we are either adding 2 chlorine or 2 bromine. And the reagent here from chlorine, you will have chlorine. And for 2 bromide, you will have bromine. So that is reagent. And usually people don't use iodine or fluorine. So this is 2 commonly used hydrogenation reagents. So where we see this before. So if you have petroleum can give you the ethane. And for ethane, if you react with chlorine, you will get addition reaction product, which is dichloride. And for some elimination reaction, you can have this sp2 carbon connect to a chlorine. And for this one, you can have a polymer reaction, open up the pi bond, connect to each other, and we will have something look like this. Okay, you don't have to know what is this reaction exactly. Is this a polymerization? And this is a PVC pipe. So that is how we make that PVC pipe that's in your household. So for the hydrogenation, the addition reaction to the alkene, this one follows so-called anti-addition. There is no Markov-Nikov addition or anti-Markov-Nikov addition because you add in the same thing. Okay, so if we start from here, and we have your bromine, and the outcome of this reaction is this 2 bromine add on to this carbon is in an anti-addition fashion. So one is on wedge, the other will be on dash. And this will give you a pair of enantiomer. So you may ask, why is that? That's come down to what is the reaction mechanism. So the reaction mechanism for this reaction is, let's use one example. For example, if we use cyclohexane as an example, I will draw this a little this way. So I basically put this like perpendicular to the paper, okay, right here. So you have this bromine get close by, so it will have a induced dipole moment. What does that mean? Okay, it's get close because this pi bond is electron, and this induced dipole moment will make the bromine that closer to the ring a little more positive charge, and the other one is more negative charge. So the pi electrons will grab the bromine to form the bond, and at the same time this will kick off, and one of the electron pair on the bottom bromine will come over, okay, to form a bond with another carbon. So the outcome of this change here is you will form a, draw this way, bromine right here, and you will form a brominium ion. Brominium ion. So it's just a mercurium ion. It's a positive charge ion. And for this ion, again, what we see here is a 3-member ring, right? 3-member ring is highly unstable. It has this positive charge. And also, you do have another bromide that break off from bromine. That's come from right here. Okay, break off the bromide. We know that bromide is a strong nucleophile, so it will attack where? This carbon right here is all relative positive charge. It's kind of stabilize the positive charge that's on the bromine. So it will come in to attack one of the carbon. In this case, there are no preference because both has the same degree of substitution. So comes in, it's like SN2 reaction mechanism. The outcome of this is the bromine that in that brominium ion now it's kind of standing up of the ring, right? And the nucleophile comes in, it's more like right here. It's at the bottom of the ring. So that explains why it is anti-addition. So it's SN2 reaction mechanism here, back attacking, that gives you the anti-addition stereochemistry. So that is one way. So when the bromine comes in, what I draw here is it coming from the top of the ring. It can also come from the bottom of the ring. So we'll draw it out right here. Kind of highlighted, meaning that this ring is perpendicular to the paper plane. So the bromine can also come in this direction, right? So it comes in from this direction. Okay, first the pi bond comes here, and one of this goes here, right? So that will give you another intermediate, and this time what you will see here is this brominium ion kind of formed like under. So you have bromine right here, positive charge, and it's under the ring right here. Okay, so when you have your bromide comes in, when you attack the same side, okay, and bromide comes in, now it's coming from the top. Kick this off, and that will give you this bromine. Blue one is at the bottom, green one now is on the top right here. That is why if you write this reaction out, if you start from your cyclohexane and with bromine, your outcome here will be a pair of enantiomer. The next reaction is the extension of halogenation. It is called halohydrin formation. So in this case, you still have your alkene as starting material, and you will have your halogen. But because bromine, for example, sometimes you will not use pure bromine as a reagent, you will put it in the solvent. And if this solvent is water or some other alcohols, instead of add 2 bromine on it, 1 bromine will be added on 1 carbon. The other carbon will get OH from water instead of bromine, and we call it halohydrin formation. So in this case, what we will have here is we'll have bromine and OH plus and it's still anti-addition, that 1 carbon got bromine, the other carbon get OH group. That is a halohydrin. So let's look at what is the reaction mechanism. So for this one, what you have here is you have bromine, right? And bromine comes in as the first step to form the brominium ion. So grab the bromine, form the bond. This also the intermediate come from this step is this brominium ion can form from the front when this bromine comes in from the paper front, or it can come from the back. Okay, and then at this moment, then what we have here is, because we have a lot of water, it's not because water is more nucleophilic compared to the bromine. It just you have a lot. When you have a lot of the water, it will compete with bromine to open that ring to have a SN2 reaction that it will attack. So it's not because it is stronger, it's just because it's a lot. So for this nucleophilic attack, the outcome here is, for the first one, what you will have is your bromine will be on the right wedge, and then because SN2 reaction mechanism, the water comes from the back attacking, so you will have OH. Okay, I should put this is the intermediate. And the same happened to the other intermediate, that now the water comes in from the front, SN2 reaction back attacking, and that will give you another intermediate. And now this H2 negative charge will be in the front. And then we will have a deprotonation process. You may ask which one we use, water or bromide. Either way, you will have something to deprotonate it, and then you will have your final product. So that is when you have hydrogen and also you have a solvent that can act as a nucleophile, then that solvent will undergo the SN2 reaction after the brominium ion formed. So let's look at another example. This example will tell you about regioselectivity, because now you are not adding the same thing on two carbons. You are adding different things. So if we start with bromine, we have bromine and we have ethanol. And what will be the product? Okay, so this will be the product. And I make this even more complicated. This will be our product, but why this is the product? Let's draw out the reaction mechanism. So you have your bromine, okay, and it will form the brominium ion. So the pi bond grab the bromine, kick this off, and it will form also the bond. So the outcome of this step again, right, you will have a brominium ion. So I need to put this in dash, this in wedge, and also you will have this in wedge and this in dash. So this bromine ion. So for these two carbons right here, the left carbon will be more positive charge. In another way to think about is because it's more alkyl group, it can stabilize that positive charge more, so making it more electrophilic. So when you have your nucleophile comes in, it will attack the more substituted carbon, okay, and that will give you bromine bromine here, and OH and SO, and you will have your wedged SO and dash methyl, and plus this one, wedged methyl and dashed SO. So what you are seeing me doing here is this bond, right? This bond break. So this is the front, basically. So this side is back. So this is front side, back side. That's why if you draw it into the stick, it's just like this. And we will keep the other group as it is. So that's an intermediate. And we'll use a deprotonation or proton transfer. You will get your product. That is the stereochemistry and regioselectivity of halo-hydrogen formation. Now we can expand the Markov-Nikov addition rule a little wider, that if we have a three-membered ring with positive charge, for example, brominium ion or the mercurium ion, what we see here is the second step nucleophile comes in, will always attack to the more substituted carbon. So instead of talking about the Markov-Nikov addition, hydrogen is adding to the less substituted carbon. We can think about that the nucleophile always add to the more substituted carbon. The next two reaction is dihydroxylation. The first one is anti-dihydroxylation. So hydroxy is OH. Di means two. So what we are adding here is two OH group on each of the carbon. And anti means that they are adding as an anti-addition fashion. So for example, if we have this alkene the reagent here is two-step reaction. The first reaction is we are going to introduce peroxy acid. Peroxy acid, sometimes we say it as RCO3H. What does that mean? Okay, so this is your carboxylic acid, right? Regular one. And we add one more, make it super reactive. This is your RCO3H, peroxy acid. So the first we use the peroxy acid, and then second reaction after the peroxy acid react with the alkene, we will introduce the acid proton source, and the outcome of this reaction is we'll have OH group both add to a carbon, and they are add as anti-addition. So this is an example. And a lot of time there is a very specific peroxy acid we use in the lab. It's called MCPBA. So that is short term. That is this compound right here. So M stands for meta. That is a meta position. Okay. And C instead stands for the chlorine. P is peroxy benzoic acid. So that is pentachloroperoxy benzoic acid. So MCPBA, if I put MCPBA as a reagent, you know that's just one of the peroxy acid that used in the anti-dihydroxylation. I will use this alkene as one example. So if we start with this alkene with MCPBA, so that is a peroxy acid, and the outcome here is you will form a epoxide. Actually, it's a pair of enantiomer. In this case, if we have this methyl in the wedge, the other methyl will be on the dash, and the other one will be this one dash, the other will be on wedge. Okay, so that is the product from the first step. Because these two methyl groups starting from the opposite side of this pi bond, so they will end up at the opposite side of the paper plane. So dash and wedge to show that. Then what happened here is a second reaction. You introduce hydronium or the proton source. So with the proton source, because this oxygen is electronegative with those lone pairs, it will get protonated and will have protonated epoxide. So this will be this pair right here. Okay. Now this looks very familiar. It just looks like the brominium ion from halogenation or the mercurinium ion from oxymercuration demercuration. So this carry positive charge and its three-member ring is higher in energy. So if at this moment you have a nucleophile, even if it's not a strong nucleophile, it will attack those carbons because this carbon will share that positive charge. And this nucleophile is water in this case. So it will come in. And in this case, the two carbons have same degree of substitution, so it really doesn't matter which one it goes. So for example, if this water comes in as nucleophile to attack this carbon, okay, SN2 reaction mechanism, so it's back attacking. So what is back attacking here? This is a bond on this side, on the top side of this bond, right? That is front. So the back will be here. So back attacking. Let's draw that out. So the outcome of that is you will have OH group on here, and you will have OH2 on here. And then methyl still pointing on the wedge, this methyl still on the dash. So that is the outcome of
this nucleophilic attack. And then, again, we will have water comes in to deprotonate this to give you the final product. The final product for this intermediate, what we will get is H. And this clearly show you that this 2 OH group or hydroxy group is add from the opposite direction. And the same will happen to this intermediate. If you have a water, okay, hypothetically attack this carbon right here, then you will end up with OH and methyl here and water. And then the final product will be OH, and methyl. So if we have a alkene, for example, like this, and we are running the reaction anti-dihydroxylation with peroxy acid, and second step use hydronium. So the outcome here is, first you can draw OH on the opposite side by showing dash and wedge, and then accordingly to put the other substitute on. So that will be our product. So now the OH on dash and wedge. So this methyl will be on wedge, this will be on dash. So that is the anti-dihydroxylation. The next dihydroxylation is the so-called syn dihydroxylation. Again, dihydroxylation add OH and add another OH, and is in a syn addition fashion. So if we start with this alkene, and the reagents here you do need to know is two-step reaction. The first step is using this osmium tetroxide. So it's catalytic amount, you don't need a lot. And then kickstart the reaction and will produce the product from the first reaction, and then we will use sodium hydrogen sulfide with water, and that will give us this molecule and also this molecule. So this is a pair of enantiomer, and it's showing you that OH group is added from the same side. From the same side, they end up at the same side, syn addition. There are also some other combination of the reagent that for the syn dihydroxylation. For example, if we start with this molecule right here, and if you have catalytic amount of osmium tetroxide, and with this molecule look like this. O minus plus, so the short name called NMO, and that will give you the syn addition, syn dihydroxylation. So if you have OH on wedge, remember you also have a methyl, so that methyl will be on dash. And if all the OH is on dash, that methyl will be on wedge. Okay, never forget the other substitute. And the same thing, for the syn addition, you can also use osmium tetroxide, and sometimes people will use this alkyl peroxide. For example, this is terbutoxide, and that also will work. And another set of reagent is if you use, okay, sort of going here, and sometimes you will also see people don't use osmium
tetraoxide because it's toxic, and we will use potassium permanganate. That is a great oxidation agent and in a basic condition, and this reaction we need to put it in cold condition for the reaction to run. So that will also give you thin dihydroxylation. So any combination of this reagent would work. So you need to be able to recognize the reaction reagents in order to determine what type of reaction it would happen. The last reaction of alkene is not an addition reaction. That is so far the first reaction that we learned to break carbon bond is called oxidative cleavage. So what happened here is if you have your alkene like this and introduce ozone, and second step use DMS. What is DMS is dimethyl sulfide. Okay, sulfide is this. And sometimes you also see people using zinc with water or zinc with HCl. All this act as reducing reagent. Okay, reducing agent. Any of this, but first step need to be ozone. And what happened here is this is your carbon on the pi bond, and it chop this off and replace on each of the carbon. Okay, I'm going to label this 1 and 2, carbon 1 and 2. So carbon 1 will become a carbon oxygen double bond, and carbon 2 will become a carbon oxygen double bond. So this is carbon 2, this is carbon 1. So that is oxidative cleavage of alkene by using the ozone and then followed by a reducing agent. So this reaction called ozonolysis. Okay, ozonolysis. And for example, if we are looking at this molecule right here, okay, and what we see is 2 pi bond. So if we throw this reagent, zinc with water this time, okay, what will happen? So because for gas reagent it's very hard to control, like 1 equivalent or 2 equivalent, so we'll assume it's always excess. That meaning wherever the reaction can happen, will happen. So if we have 2 carbon-carbon double bond, that means both will be cleaved to form carbon-oxygen double bond. And the best way to do this type of practice is to label your carbon. For example, I'm just going to random label it by, not for the naming, by random labeling to track where are your carbons. So 5, 4, 5, 6, and 7, and this is 8. So what we see here is carbon 8 will cleave or break the bond from carbon 4. So carbon 8 stands by itself. So we have carbon 8, and on carbon 8 you have also 2 hydrogens. So this is your carbon 8. And for carbon 4, you will have carbon 4, right? You will have carbon 4, and carbon 4 will connect to carbon 3, and carbon 2, and carbon 1. And 1 again is the carbon which has a carbon-carbon double bond. So that bond break, and carbon 1 will have a carbon-oxygen double bond. And from the other side, 4 connect to 5. This is your 5. And carbon 6. 6 is the one have carbon-carbon double bond. Now is cleaved to form a carbon-oxygen double bond. And carbon 7 is connected to carbon 6. So that is the second product. So through this ozonolysis reaction, you have 2 products. So this is a really good way to label your carbon and track your carbon to form your product. So that is oxidative cleavage.